talk from Keunho Kim, who will tell us about the importance of star formation in intensity in Lyman alpha escape from Green Pea galaxies and Lyman Break Analogs. So Keunho, if you could share your screen. And here we go. Yeah, there you go.
Okay, do you hear me?
Yes.
Hi everyone, I'm Keunho Kim, a PhD candidate graduating this summer at Arizona State University. First, I would like to thank the committee meeting members for giving me the opportunity to present our results. Today, I'm going to talk about the importance of star formation intensity in Lyman alpha escape from Green Pea galaxies and Lyman Break Galaxy Analogs. Okay, what are Green Pea galaxies? They are local starburst compact dwarf galaxies with typically low metallicity and low extinction for their stellar mass. They are first discovered by SDSS Galaxy Zoo project. As inferred from their nickname, their optical color is greenish due to strong O3 emission line at their redshift. These two images show two examples of Green Pea galaxies observed with SDSS color composite images. And as seen here, they are mostly unresolved with SDSS images and look like a Green Pea. Their UV spectroscopy properties have shown that most of Green Pea galaxies are Lyman alpha emitting galaxies, and thus they are known as some of the best local analogs of high redshift Lyman alpha emitters. As for local Lyman Break Galaxy analogs, they are UV continuum selected local starburst galaxies showing similar properties with high redshift Lyman Break galaxies. To this end, the motivation of this project is to investigate the spatially resolved central UV photometric properties, such as star formation intensity. In this talk, star formation intensity is the parameter is that star formation per unit area and equivalent to star formation rate surface density. And we'll investigate the possible associations with the Lyman alpha escape mechanisms, also with our measured star formation intensity. We've selected a sample of 40 Green Pea galaxies and 15 Lyman Break Galaxy analogs from the literature that are all observed with HSD COS spectroscopy and the associated near-UV acquisition images. The near-UV images have high spatial resolution in the sense that their typical point spread function is only 2 pixels, corresponding to 0.047 arcsecond. Thus, with high spatial resolution near-UV images and the physical proximity of our sample local analog galaxies, we are able to measure the central 250 parsec region star formation intensity of our sample galaxies, which is only achieved for these local analogs with high HST images. In order to do so, we accounted for redshift-dependent nonlinear effects such as PSF. And in order to account for those effects, we first performed the point spread function deconvolution against the original image. And we also removed the image noises by performing denoising procedure. And in order to only measure the uniform 250 parsec same physical region star formation intensity, we resampled pixels and then derived the Petrosian galaxy segmentation map to derive the total star formation rate from NUV images as well. This figure shows 4 different Green Pea examples. Each row shows an individual galaxy, and from left column to right columns, original COS NUV image, point spread function deconvolved, and denoised images. And lastly, we corrected for galactic Milky Way and internal extinction, as well as our measured UV star formation intensity is K corrected at the wavelength of 1877 angstrom. First of all, the measured central star formation intensity of Green Peas and Lyman Break analogs shows the mean star formation intensity of 15 and 28 solar mass per year per kiloparsec square, respectively. And this high SFI star formation intensity is 2 to 3 orders of magnitude larger than typical star forming disk galaxies. And interestingly, all sample Green Peas and LBAs have large star formation intensity larger than 0.1 solar mass per year per kiloparsec square, which is a suggested SFI threshold for generating galactic scale outflows winds. As our project aims to investigate the dependence of Lyman alpha strength and escape on star formation intensity, we directly compare our measured central SFI with Lyman alpha equivalent with, in the left panel, and Lyman alpha escape fraction. As shown in the distribution and the associated Spearman correlation coefficients within the red circles, there are no significant positive correlations with our measured SFI and Lyman alpha properties in our sample Green Peas and LBAs. However, when we consider the parameter of specific star formation intensity defined as star formation intensity divided by galaxy stellar mass, we found statistically significant positive correlations, as well as the observed increasing trend between specific star formation intensity and Lyman alpha equivalent with, as well as Lyman alpha escape fraction. And our the correlation coefficients are among the most significant among the ones we've investigated, such as with 1 over Mstar or total just specific star formation rate, as shown here. Also, interestingly, among our sample Green Peas, the conformed Lyman continuum leakers show high specific star formation intensity compared to the rest of the sample galaxies. The discussion is the high central star formation intensity in Green Peas and LBAs, which is typically 2 to 3 orders of magnitude higher than typical star-forming disk galaxies, which is satisfying the physical condition for generating galactic scale winds. And in addition to this, if we, by considering the effect of galaxy stellar mass as a proxy of gravitational potential and the associated escape velocity for gas and dust to be ejected, the parameter of specific star formation intensity as a driving parameter for Lyman alpha photon escapes can be likely related to the clearing power of ISM with holes represented by strong SFI in shallow gravitational potentials, which is likely making less chance of resonance scattering of Lyman alpha photons on their way to escape. This simple cartoon below shows how Lyman alpha photons, indicated by violet arrows, can escape from the central burst region in Green Pea galaxies, based on our specific star formation intensity explanation. So the summary is, by fully utilizing the physical proximity of local analogs, Green Pea galaxies and Lyman Break analogs, as well as the high near UV spatial resolution images, we've measured the uniform central 250 parsec star formation intensity of these local analogs of high redshift Lyman alpha emitters and Lyman Break galaxies. The measured central SFI of Green Peas and LBAs show high SFI compared to typical star-forming disk galaxies, which is well above the suggested SFI threshold of 0.1 for generating galactic scale outflows. While the central SFI alone doesn't show significant positive correlations with Lyman alpha properties of Green Peas and LBAs, we've found that the parameter of specific star formation intensity, defined as SFI per stellar mass, shows the significant positive correlations with Lyman alpha equivalence width and Lyman alpha escape fraction. And our analysis thus have suggests a Lyman alpha escape mechanism where strong galactic outflows can make significant holes in the ISM in shallow gravitational potentials through which Lyman alpha photons can ease their escape. For further details, please see our recently published paper, and also you can email me, and I'm happy to take questions. Thank you.
Thank you, Keunho. Yes, so very interesting talk. Thank you very much. And we have some questions. So Maxime asks, sorry if I have missed this during the talk, but is the SSFI, the SFR within 250 parsecs divided by the stellar mass within 250 parsecs as well, or the total stellar mass?
For, when we compare with SFR, this is the total. You mean the stellar mass? Stellar mass is the total, not only the one within
not the aperture mass. Okay.
Yeah, not the aperture ones. This is the total stellar mass.
Okay. Matt Hayes asks, if the galactic winds are important, have you made any measurements using absorption lines, such as with velocities or covering fractions?
This current analysis is focusing on the photometric aspects, but so we haven't directly checked the absorption properties yet. But yeah, that would be definitely a interesting point.
Okay. Yuki Isobe asks, could you please remind me the motivation you distinguish Green Peas and Lyman Break Analogs? What are the differences between these?
The basic difference between the two classes of these local analogs is the different sample selection technique, where Green Pea galaxies are are selected based on their strong O3 emission line imprinted in their R-band image. So they are emission line selected samples, whereas Lyman Break Galaxy Analogs are UV continuum selected samples. So although they are both local starburst galaxies, their sample selection is basically different, and which causes some differences in their physical properties as well.
Okay. Tom Toons asks, do you think the dependence on Mstar could be related to metallicity rather than halo escape velocity?
Yeah, that's a great point. And yeah, we also considered Mstar could be reflecting low metallicity effect. But when we consider the dynamic range of this specific star formation intensity, for example, here from minus 10 to the minus 9 up to 10 to the minus 6.5, which is wider than just the gas phase metallicity range. So we are more tempted to interpret this whole effect is likely caused by the linear Mstar effect, which is a gravitational potential. But yeah, we also note there are some there could be some gas phase metallicity effect, but that is only within a depth, one depth.
Right. So there's unfortunately there's a few more questions, but I think we should move on in the interest of time. So thank you, Keunho, and please do check the Slack when you get a chance, and you can see all the other questions that are there.
Yes.
Thank you very much again.